Okay, key vocabulary. Remember what we talked about yesterday? We talked about set notation. Mainly we talked about intervals, right? And the notation was how we defined those intervals, whether by number lines, as you say there, Bryce, set notation, interval notation, inequality notation. Well, here we have the definition of a domain and a range, and that definition is the domain of function f of x is a set of input values of f of x is a set of input values x. The range of function f of x is a set of output values f of x. So it's kind of like in that song, remember? The x is on the left, the y is on the right, and so that's basically what it is. Let's go on here. And now end behavior. So we just kind of skirted over domain and range. We're going to give examples of it later. Now end behavior is what we're going to really talk about. Now what do you think end behavior is? It's at the end, right? It's like, no, it's not how you behave just before you die. It's not that. It's how a function behaves. Oh, good, Connor, you laughed at me. That's good. Cut the joke. All right. See, that's how I know. That's how I know, class, if you're with me. If you laugh at my jokes, that's good. So here we have this basic function here. F of x equals x plus 1. And the end behavior of function describes what happens to f of x values as the x values either increase without bound, approaching positive infinity, or decrease without bound, or approaching negative infinity. And for instance, consider the graph of the linear function shown. And so I'm going to go ahead and go to the next slide, which gives you kind of a chart for that you can take in your notes.
Oh, dang.
All right, this gives you the description of that. One thing I will tell you about your book, and I might have mentioned this yesterday, is that in your book, it'll refer to infinity as positive infinity. Usually I don't write it that way. Usually I write it if it's positive infinity, I just write infinity. It's just like for me, if you write 5, do you need to put down a positive sign in front of the 5? No, you don't. So that's just the way I prefer to do it. But that's up to you. Okay. Ready to go to the next page here?
Not even close. The first.
I'm still in the first box.
All right, that's fine. Okay, Peyton, you're the last man standing. Right, all right,
Okay, I got it.
good. All right, so now we have example 1. Write the domain and range of the function as an inequality using set notation and using interval notation. This function here, f of x equals x squared, what kind of a function do we call that? Hey, what?
It's only 2 more times.
Hey, what? I will give you a hint. Okay, I'm going to write down a Latin word. It's the Latin word for square. That's the Latin word for square, quadratus.
Quadrilateral.
So what kind of function is this?
Quadratic.
Quadratic. This is a quadratic
Calculus.
function. And the quadratic function belongs to what larger family of functions? Starts with a P.
No.
There are positive functions. That's a trait of a function, but that's a trait of a function, but not like the larger family function is called polynomial functions. Okay. So this one over here, this linear function is also a polynomial function. It's x plus 1. Anyway, and that's important for knowing domain and range, because the domain, and here it says write the domain. The domain of any type of polynomial functions is, what's the domain of any type of polynomial function? What is the domain of any type of polynomial function? Well, it's this. It's all real numbers, and we can write it like this. X is greater than negative infinity, less than infinity. There it is. Okay, what is our set notation going to be for this? And you can copy this down, or you can do this thing we talked about, right? Did we talk about this?
Yeah.
Yesterday we did, okay. In an interval notation, what does interval notation consist of? Brackets and parentheses, right? Brackets, parentheses, a comma, some numbers, pretty much it. So what is this going to be here for interval notation? Parentheses. So there it is, okay? And what is our range of this function going to be? Zero. So Bryce says we start at 0. Is that right? Yeah, I think that's good. And then actually it's y, right? Is y greater than 0 or greater than or equal to 0? Greater than or equal to 0. And less than infinity. And a set notation, we have y such that y is greater than or equal to 0. And then, so that's inequality notation here. This is set notation. And what is our interval notation? Is this our interval notation?
Didn't you put the brackets?
Okay, yeah, thank you, Jaden. Okay, Jaden caught my mistake. Good job. Yes. Sometimes I do that deliberately, sometimes not. Okay, and end behavior.
Why you put the bracket instead of the parentheses?
Okay, good. He's asking the follow-up question. Why? Yeah, because 0 is actually part of the output values, right?
Okay.
In fact, if we did like an XY table here, and we plugged in zeros in input, we would get zeros in output. Okay, so that's why. Okay, so it actually can be 0. And now for end behavior, as x approaches infinity, what does f of x approach?
Infinity 0?
Also infinity, okay? As x approaches negative infinity, f of x approaches what? Negative infinity, you say? Is that right? Okay, I'm looking for negative infinity. I'm not seeing anything. I'm not seeing anything.
Wait, it'd be 0, right? Because it doesn't go below.
So we go as f goes like this, right? As x goes like this, what happens to the y values?
They decrease? No, they stay the same. So it'd be
Are they increasing or decreasing?
same. The y values?
Yes.
They're staying the same because it's flat.
What is flat about this graph? I don't
Oh, you're
see
talking about
this.
the curve? They're talking about the arrow that he pointed.
Okay, Marcus told me.
He's confused with being straight.
Marcus just told me this, right? Marcus, is that what you told me, Marcus?
Yes, sir.
Yeah, so anyway, so this is an example where your end behavior is the same no matter which way you go, okay? And basically, we call this is what we call an even function. And an even function will have reflect about the y-axis. So in this case, this one starts high and ends high, right? And what about y equals x? What does that look like?
Yes.
Starts low and ends high, right? So odd positive, and this is an odd negative function. This is even positive, and which way is even negative?
Down.
Down. Okay, yeah, Jay. So, yeah. So that's basically it. We're going to get into that more later this year and next year for those of you taking pre-calculus. All right. So basically, that's it. Now, to me, the strange thing here is that when we evaluate functions, we're usually evaluating functions in what direction? Like the vertical line test. What do you do with the vertical line? Move it which way?
Right.
Left to right, okay? But in this case, you're approaching negative infinity, looking for end behavior the other way. So it might be a little bit strange or counterintuitive to how you're accustomed to looking at algebra. But here we do that, all right? What I want you to do is, it says example 1 here, but really this is example 2. I want you to go ahead and try to fill this out for this exponential function. Now, in pre-calculus, we're going to see f of x equals e to the x, but this is a very closely related function, and the basic traits are the same. So go ahead and fill that out, and I'll go over that with you in a couple minutes. Okay, for this one here, is the domain for this function going to be the same as for the last one we had? Yeah, it's going to be all real numbers, right? So it's going to be like this. Greater than negative infinity, less than infinity. Set notation, x such that x is an element of all real numbers. And our interval notation is going to be also. So here we've seen nothing different, right? It so happens that most parent functions that we see in algebra just happen to be all real numbers, but not all. Okay? Just depends on the situation. What is the range of this function? What is y greater than? Greater than 0? Or is it greater than or equal to 0?
Equals, greater than.
You think greater than or equal to? Okay. Does y actually ever equal 0 in this function? No, it doesn't. So we have to alter this a little bit, don't we? What is this actually going to be? It's going to be this thing here, right? Does that look a little better now? Yeah, it looks a little better. Okay. Okay, that's the way it's supposed to look. All right. And what about set notation? Y such that y is greater than 0. Okay. Interval notation going to be like this, right? Oops. What do we put here first? 0, right? And now what about end behavior? As x approaches infinity, what does f of x approach? Infinity, Marcus says. Does that sound right? Okay. Now as x approaches negative infinity, f of x approaches, what do you think goes here?
Infinity?
What are we approaching as x approaches negative infinity?
0, 0.
0. This one thing that, this line here, which is the equation y equals 0, is the equation of what we call a horizontal asymptote. You ever heard of what a horizontal asymptote is, or an asymptote? You haven't heard of that? Okay, what it is, it's the limit as x approaches positive infinity or negative infinity. That's what it is. In this case, we have a horizontal asymptote. On my discontinuities t-shirt, I happen to have drawn a function that has a vertical asymptote and a horizontal asymptote. And I will show this to my viewers. Okay, so you got a horizontal asymptote, looks like here y equals 0, or isn't y equals 0? Is it 1/2? I think it is 0 actually. And then the vertical asymptote at x equals 2. Okay? Yeah, this horizontal asymptote is y equals 0. Okay, questions on this?
On the range inequality then, why is it not greater than or equal to, or less than or equal to? I mean, I meant less than or equal to.
You mean right here?
Less than- No, on the inequality,
Inequality.
top range.
Who-
Any on the range.
Range and inequality.
Yeah, that one. why wouldn't that be greater or less than equal to? And why is it less than?
Because the zero, the line never reaches zero.
Oh, yeah, I remember this question.
Yeah, and if you go to a calculator, for example, you could put that in a calculator. Let me put that in my calculator right now to show you. Okay, y, here it is. We'll have 2 to the power of x, right? And if we go to the table view, I'll go to zoom 6, so we can see it right here. Now it looks like touches 0, right? We go to the, oops, I have the wrong, I want to go to auto. So now we go to second graph. So we see, so here, you can see the numbers are getting smaller, but are they actually touching 0? See, they're getting really minuscule, right? This right here, to the negative 9th power, that's what? That's trillionths, okay? Really small numbers. 3.7 times 10 to the negative 9th power, 3.7 trillionths. Is that pretty close to 0? Yeah, but is it 0? No, not quite. Okay. And then the question 4, why is the end behavior of a quadratic function different from the end behavior of a linear function? And here's a little sketch of a quadratic function. Here's a sketch of a linear function. Why are they different?
One's a unit, one's a straight line.
Yeah, the shape is different, right? So the shape or nature of those functions, each of them, is different. So that's it. So really, that's